Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
Voyager 1, the farthest man-made interstellar object in outer space, has already unveiled stunning discoveries like the secrets behind Jupiter's rings and the unexpected behavior of the heliopause. But now, after an incredible 45 years of exploring space, the spacecraft is sending back signals that could change how we understand our solar system. It's uncovering astonishing findings, including strange ripples in the heliosphere, revealing just how dynamic and turbulent this region is, much different from what scientists initially believed. And there's something unusual happening with Voyager's systems too. It's still operating, but some of the data it's sending back doesn't make sense. How is it still working while showing signs of malfunction? Could this indicate that it's encountering something we didn't expect? Are they hinting at the possibility of alien life or revealing new cosmic mysteries? Join us as we explore the impossible discovery Voyager 1 has made that has surprised the scientists and what it could mean for our universe. The history of Voyager 1, a journey beyond the solar system. NASA launched Voyager 1 on September 5, 1977, marking the beginning of one of the most ambitious space missions in human history. Voyager 1, along with its twin Voyager 2, was designed to explore the outer planets of our solar system, Jupiter and Saturn, and then continue onward, perhaps into the unknown regions of space. Its primary mission was to collect and transmit data about these planets, their moons, rings, and magnetic fields, as well as providing close-up images of the gas giants. But no one could have predicted how far Voyager 1 would eventually travel, nor the groundbreaking discoveries it would make along the way. The spacecraft was equipped with a suite of sophisticated instruments that allowed it to measure various phenomena in space. Its payload included an imaging system designed to take pictures of Jupiter and Saturn and their moons, a magnetometer to measure magnetic fields, a plasma detector to analyze the density and temperature of charged particles, a cosmic ray detector to study cosmic radiation, and a radio science system which provided detailed data on the planet's atmospheres and rings. Voyager 1's grand tour of the outer planets was nothing short of revolutionary. The spacecraft's trajectory was carefully planned to utilize gravity assists from Jupiter and Saturn, a technique that allowed it to gather speed without using additional fuel, essentially slingshotting around the planets. This allowed Voyager 1 to travel much farther than any previous spacecraft, all the while sending back an unprecedented wealth of data to Earth. Voyager 1's closest approach to Jupiter occurred on March 5, 1979, a mere 18 months after its launch. This encounter provided humanity with its first ever detailed images of the largest planet in our solar system. One of the most stunning revelations from this encounter was Jupiter's rings, which had never been observed before. Until then, it was believed that only Saturn had a ring system, but Voyager 1 revealed that Jupiter too was encircled by faint rings composed mostly of tiny dust particles. These rings are much less prominent than Saturn's, but their discovery changed our understanding of the gas giant and raised new questions about how such rings form. Voyager 1 also captured detailed images of Jupiter's Great Red Spot, a colossal storm larger than Earth that had been raging for at least 4 centuries. These images gave scientists new insights into the structure and dynamics of the storm, revealing strong winds swirling in opposite directions around its center. The Great Red Spot was found to have wind speeds exceeding 400 miles per hour, making it one of the most powerful weather systems ever observed. In addition to the Great Red Spot, Voyager 1 discovered other smaller storms and weather phenomena on Jupiter, including lightning and auroras. These findings revealed similarities between Jupiter's atmospheric dynamics and those of Earth, even though Jupiter's atmosphere is composed mostly of hydrogen and helium, vastly different from Earth's nitrogen-oxygen mix. The discovery of lightning storms on Jupiter was particularly surprising, as they suggested that despite its gaseous nature, Jupiter experiences weather phenomena akin to thunderstorms on Earth. Another groundbreaking discovery from the Jupiter flyby was the observation of Io, one of Jupiter's moons, which was found to be the most geologically active body in the solar system. Voyager 1 observed volcanoes erupting on Io, spewing sulfur and sulfur dioxide hundreds of miles into space. This was the first time active volcanism had been observed on a body other than Earth, and it suggested that Io's interior was heated by tidal forces exerted by Jupiter's immense gravity. Voyager 1's flyby of Saturn occurred on November 12, 1980, marking another milestone in its journey. Saturn had long fascinated astronomers with its stunning ring system, but Voyager 1 provided the first detailed close-up images, revealing that Saturn's rings were far more complex than previously imagined. Rather than being a single continuous structure, Saturn's rings were found to consist of countless individual particles, ranging in size from tiny grains of dust to boulders several meters across. These particles orbit Saturn in intricate patterns, creating gaps, divisions, and waves within the ring system. The images also showed that the rings are not static, but are influenced by the gravitational interactions between Saturn's moons and the ring particles. Voyager 1's observations of Saturn's largest moon, Titan, were equally groundbreaking. Titan had long intrigued scientists because it is the only moon in the solar system with a dense atmosphere. Voyager 1 discovered that Titan's atmosphere is composed primarily of nitrogen, with small amounts of methane and other hydrocarbons, making it similar in some ways to the early atmosphere of Earth. However, the thick haze surrounding Titan prevented Voyager 1 from obtaining clear images of its surface, leaving the mystery of what lies beneath its clouds unsolved for decades, until the Cassini-Huygens mission in 2004. Voyager 1 also discovered new moons around Saturn, including Prometheus and Pandora, which were found orbiting near Saturn's F-ring. These moons, known as shepherd moons, help to maintain the shape and structure of Saturn's rings through their gravitational influence. The discoveries made by Voyager 1 during its encounters with Jupiter and Saturn fundamentally changed our understanding of the solar system. Before the Voyager missions, little was known about the outer planets beyond what could be observed from Earth-based telescopes. Voyager 1's observations also paved the way for future missions, such as Galileo to Jupiter, Cassini to Saturn, and the planned Europa Clipper mission to explore one of Jupiter's most intriguing moons. Although Voyager 1's primary mission was originally expected to last just 5 years, the spacecraft has continued to function for over 45 years, thanks to the remarkable durability of its components and the ingenuity of NASA's engineers. Voyager 1 is powered by radioisotope thermoelectric generators, RTGs, which convert the heat generated by the decay of plutonium-238 into electricity. While the power output from the RTGs has decreased over time, Voyager 1 has continued to operate by shutting down non-essential systems and using backup systems that have remained functional for decades. For example, in 2017, NASA successfully activated thrusters that had been dormant since Voyager 1's last planetary encounter in 1980. But if Voyager 1's journey through the solar system was already filled with astounding discoveries, what could its latest impossible signals from interstellar space reveal? Is there something far more mysterious lurking beyond our solar system than we ever imagined? The impossible discovery, mysterious signals from Voyager 1. In May of 2022, NASA announced that Voyager 1, the farthest human-made object in space, had begun transmitting puzzling and inexplicable data from its Attitude Articulation and Control System, AACS. The AACS is a vital component responsible for controlling Voyager 1's orientation in space. This system ensures that the spacecraft's high-gain antenna remains pointed toward Earth, allowing it to send data and receive commands despite being more than 14 billion miles away from home. However, Voyager 1's AACS began sending back garbled telemetry data, baffling scientists. Despite the erroneous data, the spacecraft seemed to continue functioning normally. The signals indicated that the AACS believed it was in an impossible orientation, yet Voyager 1 was still receiving commands, executing them correctly, and transmitting scientific data back to Earth with the same signal strength as before. This paradox led NASA to a troubling question. How could the AACS be malfunctioning while the spacecraft still appeared to be operational? Suzanne Dodd, project manager for both Voyager 1 and its twin, Voyager 1, at NASA's Jet Propulsion Laboratory, JPL, commented on the situation. A mystery like this is sort of par for the course at this stage of the Voyager mission. The spacecraft, now in interstellar space, is exposed to levels of cosmic radiation that no spacecraft has ever encountered before. As Dodd explained, we're in a high radiation environment that no spacecraft have flown in before, raising the possibility that radiation might be affecting Voyager's systems in ways not fully understood. The malfunction in the AACS presented a conundrum. While the system's telemetry data was effectively junk, Voyager 1 had not triggered its safe mode, a protective state where the spacecraft powers down all non-essential systems to allow engineers to diagnose and fix problems. This indicated that the spacecraft itself did not recognize the AACS data as faulty, further complicating the mystery. The investigation into Voyager 1's AACS malfunction began with a significant challenge: the immense distance between the spacecraft and Earth. At more than 14.5 billion miles, around 23 billion kilometers, away, signals sent from NASA's Deep Space Network, DSN, to Voyager 1 take approximately 20 hours and 33 minutes to reach the spacecraft. A response from Voyager 1 takes just as long, meaning every communication between Earth and Voyager involves a delay of more than 41 hours. This creates a painstakingly slow process of troubleshooting, as engineers must wait nearly 2 days to receive data following each command sent to the spacecraft. Despite this delay, NASA engineers embarked on diagnosing the issue. The first step was to determine whether the problem lay solely with the AACS or if it involved other systems as well. As part of this investigation, engineers sent commands to reboot the AACS and execute different diagnostic routines, hoping to identify the source of the errant telemetry data. One theory proposed by NASA's engineering team was that the AACS might be affected by cosmic radiation in the interstellar medium, the region beyond the heliosphere, where Voyager 1 has been traveling since 2012. This area of space is filled with charged particles from exploded stars, known as supernovae, which create a high radiation environment. The spacecraft's systems, now operating in uncharted territory, may be experiencing issues from prolonged exposure to this intense radiation. Additionally, Voyager 1's systems, which were designed to last only 5 years, have far outlasted their expected lifespan. To conserve energy, NASA has gradually turned off various non-essential systems and scientific instruments aboard Voyager 1, yet the AACS remains one of the most critical systems. By 2025, Voyager's power levels will drop to the point where NASA will have to make further cuts to keep the spacecraft operational. However, this power reduction did not seem to be the cause of the current AACS malfunction, as all systems were still receiving sufficient energy to operate. Suzanne Dodd remained cautiously optimistic. "I think if there's a way to solve this issue with the AACS, our team will find it." To better understand the AACS malfunction, NASA engineers compared the garbled telemetry data with previous readouts from when the system was functioning correctly. This analysis helped the team pinpoint inconsistencies in the system's code and assess whether it was a software glitch or a deeper hardware failure. Despite the spacecraft's advanced age, the engineering team continued to explore potential solutions, including rebooting the AACS or rerouting control to backup systems, as was done with other subsystems in the past. One of the perplexing aspects of this issue is that while the AACS telemetry is invalid, Voyager 1's high-gain antenna remains correctly pointed toward Earth. The strength of the signal suggests that the spacecraft is still properly oriented, despite what the faulty data indicates. This raises the possibility that the issue might not lie within the AACS itself, but could be caused by another system interfering with its telemetry. Another potential explanation could involve memory corruption due to cosmic rays, which might be affecting how data is stored and transmitted. Cosmic rays, high-energy particles that originate outside the solar system, can penetrate spacecraft electronics, sometimes causing bit flips or data corruption in memory. Voyager 1, now traveling through interstellar space, is exposed to more cosmic rays than it was within the protective bubble of the heliosphere, increasing the likelihood of such radiation-induced malfunctions. As of March 2024, NASA had not yet pinpointed the exact cause of the AACS malfunction. However, the investigation was ongoing, and engineers remained hopeful that a solution could be found. In the meantime, Voyager 1 continues to transmit valuable scientific data, expanding humanity's understanding of the cosmos beyond the boundaries of our solar system. But what if the strange signals are just the beginning? What new mysteries could Voyager 1 uncover as it probes the turbulent, ever-shifting boundary between our solar system and the uncharted depths of interstellar space? Ripples in the heliosphere. The heliopause marks the outermost boundary of the solar system, where the solar wind charged particles emitted by the Sun collides with the vast interstellar medium. Essentially, the heliopause is a protective bubble created by the Sun's magnetic field that encases our entire solar system. Inside this bubble, known as the heliosphere, the solar wind dominates, while beyond it lies interstellar space, where the influence of the Sun weakens and the forces of the galaxy take over. Voyager 1 was the first spacecraft to breach this boundary, entering interstellar space on August 25, 2012, after traveling over 11 billion miles from Earth. The crossing of the heliopause represented a monumental achievement, as it was the first time any human-made object had left the solar system. However, as Voyager 1 ventured farther into interstellar space, it began to detect unexpected phenomena at the heliopause that surprised scientists back on Earth. One of the most significant discoveries Voyager 1 made in the years following its entry into interstellar space was the detection of ripples in the heliopause. These ripples suggest that the boundary between the heliosphere and interstellar space is not smooth or static as once thought, but rather a dynamic and fluctuating region. This discovery came as a shock because the heliopause had long been considered a relatively stable barrier, with the solar wind gradually tapering off as it met the interstellar medium. The ripples Voyager 1 detected indicate that the heliopause is subject to external forces, such as shock waves from supernova explosions in distant parts of the galaxy. These shock waves send powerful bursts of energy through the interstellar medium, which in turn interact with the heliosphere. When these waves collide with the heliopause, they create disturbances or ripples that can be detected by instruments aboard Voyager 1. In particular, Voyager 1's plasma wave instrument played a critical role in identifying these ripples. Plasma waves are fluctuations in the density and movement of charged particles, and they can be used to map out the structure of the heliopause and the regions beyond. In 2014, data from Voyager 1 revealed that the spacecraft had passed through several of these ripple events, providing the first concrete evidence that the heliopause is a dynamic boundary. The timing of these ripple detections was also significant. Voyager 1 encountered multiple ripple events between 2012 and 2014. As these waves traveled through the interstellar medium, they disturbed the edge of the heliosphere, causing the heliopause to shift and ripple in response. One of the most important implications of this discovery is that the heliosphere is constantly interacting with the surrounding interstellar environment. The Sun's magnetic field, which extends far beyond the orbit of Pluto, is not strong enough to fully isolate the solar system from the rest of the galaxy. Instead, the heliopause serves as a kind of semi-permeable membrane, allowing some particles and energy from interstellar space to pass through. This has significant consequences for the Earth and the other planets within the solar system. For example, the galactic cosmic rays that bombard the solar system from distant supernovae and other cosmic events are influenced by the structure of the heliopause. When ripples form in the heliopause, they can either block or allow more cosmic rays to enter the solar system, potentially affecting planetary atmospheres, including Earth's. This discovery provides a new framework for understanding how cosmic radiation might impact life on Earth and how the solar system's position within the galaxy changes over time. Moreover, the detection of ripples in the heliopause opens up new avenues of research into the nature of interstellar space itself. The interstellar medium, once thought to be a relatively homogeneous environment, is now understood to be a turbulent and ever-changing region, influenced by shock waves, magnetic fields, and cosmic events. Voyager 1's data suggests that the interstellar medium is more complex than originally believed, with regions of varying density, temperature, and magnetic strength. Scientists are also beginning to explore the possibility that the heliosphere, rather than being a simple bubble, may have a tail that extends far beyond the heliopause. This tail could be shaped by the Sun's movement through the galaxy and by the interactions between the solar wind and the interstellar medium. Another important aspect of Voyager 1's discovery is that the Sun's activity, including solar flares and coronal mass ejections, can cause the heliosphere to expand and contract, altering the position of the heliopause. NASA is currently planning future missions to explore these regions in greater detail, including the Interstellar Mapping and Acceleration Probe, IMAP, which is scheduled to launch in 2025. IMAP will build on Voyager 1's discoveries, providing more detailed measurements of the heliopause and the surrounding interstellar medium. If Voyager 1 could reveal the heliopause's shifting nature, what other hidden forces might be at play in navigating the immense gravitational pulls of giant planets like Jupiter and Saturn? Why hasn't Voyager 1 been pulled by planetary gravitational forces? One of the most common questions about Voyager 1 is, how did this small spacecraft manage to avoid being pulled into the massive gravitational forces of planets like Jupiter and Saturn? Voyager 1's journey through the solar system involved flying past some of the most massive planets, particularly Jupiter and Saturn, whose gravitational fields are extremely powerful. Jupiter, the largest planet in the solar system, has a mass over 317 times that of Earth, and its gravitational pull is so strong that it exerts a strong influence on its many moons and the asteroid belt. Similarly, Saturn, with its iconic rings, possesses a gravitational field that could easily trap any spacecraft passing nearby. The key to Voyager 1's successful journey lies in the use of a technique known as the gravitational slingshot, or gravity assist. This maneuver uses the gravitational pull of a planet to accelerate a spacecraft and alter its trajectory without using additional fuel. The concept might seem counterintuitive at first. How can something be propelled forward by a planet's gravity, which normally pulls objects inward? Here's how it works. As Voyager 1 approached a planet like Jupiter, it was pulled in by the planet's gravity. However, instead of getting trapped, the spacecraft's trajectory was carefully calculated so that it would pass by the planet at just the right angle. As Voyager 1 neared Jupiter, the planet's immense gravity accelerated the spacecraft, increasing its speed significantly. By the time it slingshotted past the planet, Voyager 1 was traveling faster than when it entered the planet's gravitational field. This technique allowed Voyager 1 to escape Jupiter's gravitational pull and continue on its journey deeper into space. Voyager 1's flyby of Jupiter on March 5, 1979, is a textbook example of how effective this technique can be. When it approached Jupiter, the spacecraft was traveling at approximately 35,000 miles per hour. After the gravity assist maneuver, it left Jupiter's orbit at a speed of over 43,000 miles per hour. This dramatic increase in velocity was crucial in propelling Voyager 1 toward its next destination, Saturn. At Saturn, a similar gravity assist maneuver was executed on November 12, 1980. Once again, Voyager 1's trajectory was carefully calculated so that it passed close enough to the planet to gain speed without being pulled into its gravitational well. After slingshotting around Saturn, Voyager 1's velocity increased even further, allowing it to escape the pull of both planets and continue on its interstellar mission. The success of Voyager 1's journey hinged on the meticulous planning of its trajectory. NASA engineers spent years calculating the exact path the spacecraft needed to take in order to use the gravitational forces of Jupiter and Saturn to its advantage. This involved predicting not only the positions of the planets at the time of the flybys, but also their motions through space, the influence of their moons, and the effects of their magnetic fields. The timing of Voyager 1's launch was no accident. The spacecraft was launched during a rare alignment of the outer planets, known as the Grand Tour Opportunity, which occurs only once every 175 years. This alignment allowed Voyager 1 to visit both Jupiter and Saturn, using gravitational assists, and then continue outward to interstellar space without the need for excessive fuel. Without this precise timing, Voyager 1 would not have been able to complete its mission or travel as far as it has today. In fact, one of the most impressive feats of the Voyager mission is that both Voyager 1 and its twin, Voyager 1, followed paths that allowed them to use the gravitational pull of multiple planets to extend their journeys. Voyager 1, for instance, used gravity assists from Jupiter, Saturn, Uranus, and Neptune, becoming the first spacecraft to fly by all four of these gas giants. Moreover, Voyager 1's onboard systems, including its attitude control system and thrusters, played a crucial role in maintaining its course. The spacecraft needed to make small adjustments to its orientation and trajectory to ensure that its path through space remained accurate. Even minor deviations could have sent Voyager 1 into a collision course with one of the planets or their moons. NASA engineers programmed the spacecraft to make these corrections autonomously, ensuring that it stayed on course throughout its long journey. But as Voyager 1 continues its silent journey, what clues might it carry about humanity's place in the universe? Could the golden record it bears offer answers or raise even more intense questions, if discovered by alien civilizations? Voyager 1 as a time capsule. One of the most unique and fascinating aspects of the Voyager 1 mission is its role as a time capsule for humanity. On board the spacecraft is the Golden Record, a copper disc coated with gold, intended to communicate with any potential alien civilizations that may encounter Voyager in the distant future. This record contains a curated selection of sounds and images that were chosen to represent life on Earth, capturing a snapshot of humanity's existence at the time of Voyager's launch in 1977. The Golden Record was designed by a team led by Carl Sagan, a renowned American astronomer and science communicator. The record contains a wide variety of content, including 115 images, natural sounds, like the sounds of wind, thunder, and birds, music from different cultures, and spoken greetings in 55 languages. These images and sounds were selected to show the diversity of life and culture on Earth, along with basic scientific information about our planet and solar system. Notable musical pieces on the record include compositions by Johann Sebastian Bach, Ludwig van Beethoven, and even a traditional song from Peru. The purpose of the Golden Record is both symbolic and practical. It serves as a message in a bottle, representing humanity's desire to communicate with any intelligent life that may one day discover it. While the chances of another civilization finding and understanding the record are incredibly slim, the act of including it aboard Voyager 1 shows the human drive to explore and share knowledge with the universe. One of the more playful speculations that has emerged from the public is the idea that aliens might already be interacting with Voyager 1. Some commenters have humorously asked, what if aliens are messing with Voyager? While this is purely speculative, it provides an opportunity to explore the broader concept of extraterrestrial life and Voyager 1's potential role as humanity's ambassador in space. The spacecraft is traveling at a speed of 38,000 miles per hour and will take about 73,000 years to approach the nearest star system, Proxima Centauri. If an alien civilization were to encounter Voyager 1, they would likely first be intrigued by the Golden Record and the message it carries. The record's contents were carefully selected to ensure that any intelligent beings who come across it might understand the fundamental aspects of life on Earth. For example, the images on the record include depictions of Earth's geography, human anatomy, and scientific diagrams explaining concepts like DNA and the structure of our solar system. By incorporating these scientific elements, the creators of the Golden Record hope to establish a common ground with any potential alien life forms, regardless of their understanding of Earth's languages or cultures. The inclusion of greetings in 55 different languages, from ancient Sumerian to Mandarin Chinese, highlights the rich cultural diversity of human civilization. These greetings were recorded by speakers from various backgrounds, emphasizing that Earth is home to a vast range of cultures, each with its unique language and perspective on the world. Despite the fact that the Golden Record was launched more than 45 years ago, it remains a source of inspiration for those who dream of space exploration and the search for alien life. The implications of Voyager 1's impossible discovery could reshape our understanding of interstellar travel and the very nature of space itself. As this brave spacecraft pushes the boundaries of exploration, we are left to wonder what other secrets it may uncover in the vast expanse of the cosmos. Could there be more surprises waiting just beyond the horizon? If you found this exploration into Voyager 1's journey captivating, don't forget to like, share, and subscribe for more mind-bending insights into space exploration. What do you think Voyager 1 will reveal next, and how will it change our perception of the universe? Share your thoughts in the comments below.